Chapter 10 focuses on the information that we can gain from drawing Lewis structures, mainly the shape and polarity of our molecules. We'll also look at hybridization and the types of bonds that are formed. When we draw Lewis structures, we are identifying where the electrons are found in our molecule. This helps us to identify electron groups, which are either bonds or lone pairs. Because these are made out of electrons, they are going to repel each other and want to be as far apart as possible. This leads to a theory, which is called valence shell electron pair repulsion. So this we abbreviate as VSEPR, valence shell electron pair repulsion. Essentially, our bonds and our lone pairs are going to move as far apart as possible in space, away from each other, in order to identify the shape of our molecule. When we're trying to identify the shape, we need to consider electron groups. And so electron groups are the pairs of electrons that are found around our central atom. Each lone pair counts as one electron group, and each bond counts as one electron group. And this doesn't matter if it is a single bond, a double bond, or a triple bond. It all counts as one electron group. So if we look at our center nitrogen, we have 3 electron groups. One is a lone pair, one is a single bond, and one electron group is a double bond. If we look at our left oxygen, we have 3 electron groups, 2 that are lone pairs and 1 that is a double bond. And on our right oxygen, we have 4 electron groups, 3 that are lone pairs and 1 that is a bond. When we're assigning the shape of a molecule, we do focus on that center atom. When we look at the shape around our center atom, we will notice that there is a difference if all of the atoms are bonds or if we have lone pairs that are present. If we look at an example, which is methane, we have the same atoms all attached around a center carbon. In this case, this is a tetrahedral shape, and we'll look at this and why that is in a little bit. But our bond angle is 109.5 for tetrahedral. So between every hydrogen, carbon, and hydrogen, we have a difference of 109.5 degrees. If we have a molecule with a lone pair, and although it's not drawn in the shape of the molecule, it is there. So we have electrons, a lone pair of electrons that are on the nitrogen. These affect the shape and the bond angle. That lone pair actually pushes the bonds a little bit closer together because they are more greatly repelled by that lone pair. And it makes our bond angle less than 109.5. You will not have to know the exact angle, but you should understand that when a lone pair is present, it makes the bond angle smaller than the ideal bond angle. If we have more than one lone pair, so in this case we have water, which has 2 lone pairs present on that oxygen, those lone pairs have a greater repulsion for one another, and so they push the bonds even closer together. So again, this is going to be less than our ideal angle of 109.5 because of the presence of the lone pairs. So the lone pairs have a higher priority, more repulsion, than our bonds do. If we look at our electron and molecular geometries, these are two different classifications. So the electron geometry is considering all of the electron groups around the atom. So we see, and I say C in parentheses, the lone pairs as a point on our shape. If we look at the molecular geometry is only seeing the bonded atoms that are present. So you'll notice in some cases, the molecular geometry is different than the electron geometry. The way we determine what the shape is and the bond angle depends on the number of electron groups. So if we look at our first example where we have two electron groups, and they are both bonding with no lone pairs on our center atom, we are going to have a linear shape. Our example is carbon dioxide. The carbon is in the center with no lone pairs. We have two electron groups, which are two double bonds, and we form a linear molecule, a line. Our bond angle from one bond to the other is 180 degrees. If we look at our next case where we have three electron groups and all three of them are bonding, our electron geometry and our molecular geometry are the same because they are all atoms surrounding that center atom. It is trigonal planar. So trigonal because we have three outside atoms, and planar because they all exist in the same plane of space. Our bond angle in this case is 120 degrees between our bonds. We do have the case where we can have a trigonal planar electron geometry, so three electron groups, but only two of them form bonds and we have a lone pair. When this is the case, when we look at our electron geometry, it's trigonal planar, but when we look at the molecular geometry, we no longer see that lone pair as a point on the shape. We're only seeing the bonds, and so this is considered a bent molecule because the lone pair is repelling the bonds, making it bent. The bond angle is less than 120 degrees. We now have the case where we have four electron groups. If they are all bonding, our shape is tetrahedral. And our molecular geometry is also tetrahedral when they are all bonds. The reason for this is if we put flat sides on each of the faces, it would be a tetrahedron. So we call it tetrahedral. The bond between, or the angle between the bonds is 109.5 degrees between each bond. We can also have the case where three are bonds and one is a lone pair. An example of this is ammonia. This is tetrahedral for our electron geometry, but because we no longer see that fourth bond, it becomes trigonal pyramidal. So trigonal pyramidal because we don't see the lone pair that is present as a point in space. And the reason it's pyramidal, because it forms a pyramid, that nitrogen is slightly higher above the plane that the hydrogens are sitting in. So it forms a small pyramid. And trigonal because there are three hydrogens attached. This does decrease the bond angle, and so our bond angle between our hydrogens for this example, would be less than 109.5. Another case we can have is two bonding groups and two lone pairs, as in the case of water. We have a tetrahedral electron geometry, but we have a bent molecular geometry because we do not see the lone pairs as points on the shape. The lone pairs push the bonds closer together, so our bond angle is going to be even smaller than it was for our trigonal pyramidal. And those lone pairs are not observed, but we do have a smaller bond angle, in this case between the hydrogens on our water molecule. If we look at the case where we have 5 electron groups with all 5 of them bonded, we call this trigonal bipyramidal. So trigonal because we have 3 atoms around the center. This we refer to as the equatorial atoms. We also have 2 axial atoms as well. And if we look at this, this kind of looks like 2 pyramids stacked on top of each other, which is where the trigonal bipyramidal comes from. The bonds between our equatorial atoms are 120 degrees, and the bond between the axial and the equatorial is 90 degrees. If we have one lone pair in our trigonal bipyramidal electron geometry, that lone pair, in order to stay as far away from the other elements, ends up being on the equatorial position. And so this, when we name this molecular geometry, we call this seesaw, like in a playground, like a teeter-totter seesaw, because of it looks like a fulcrum with a plane. This one is drawn sideways, but it is known as a seesaw geometry. And our bonds get squished a little bit closer to each other, so our bond angles are slightly smaller. If we have 3 bonds and 2 lone pairs, again, these lone pairs happen around the equatorial positions, and the resulting molecular shape is T-shaped. Our lone pairs are on that center atom, pushing our axial and the one equatorial bond that remains closer together, making our bond angle less than 90 degrees. If we have the case of having 3 lone pairs, all 3 of the lone pairs are found on the equatorial position. This leaves the 2 axial atoms so they can be as far apart as possible. And this results in a linear shape with a bond angle of exactly 180 degrees. So we can have a trigonal bipyramidal electron geometry and a linear molecular geometry if we have 3 lone pairs around our center atom. Now, all of these cases can only happen if we are in row 3 or below. And the reason for that is because we have to have our expanded octet. The previous slide, we can be in row 2, and so those are probably going to be the more frequent geometries that you see are the ones on the previous slide. These happen only if we're in row 3 or below. If we have 6 electron groups around our center atom, and all 6 are bonded atoms around that center atom, we call this octahedral because the resulting shape, if we put sides on between our atoms, would be an octahedron. So this is octahedral. Our bond angles are all 90 degrees. And we can add lone pairs here as well. So if we have one lone pair, it becomes square pyramidal because the lone pair is no longer observed. And it pushes the bond angles a little bit closer so they are less than 90 degrees. If we have two lone pairs, this is a square planar shape because those lone pairs are going to want to be as far apart as possible, leaving our bonds around what would essentially be the equator of our molecule. And because those lone pairs are both repelling the bonds equally, our bond angle remains 90 degrees for our square planar molecule. So these are the shapes that our molecules can take based on the Lewis structures that are drawn and the electron groups that are around it. Remember, an electron group is any lone pair, any bond, whether it be double, single, or triple. Predict the geometry and bond angles of PCl5. In order to figure out the geometry and bond angles, we need to draw the Lewis structure. So phosphorus has 5 valence electrons, and chlorine, each chlorine has 7. So we have 26 electrons to work with. We're going to put the phosphorus in the center. We're going to draw our chlorines around it. Put a bond to each chlorine. Leaves us with 20 electrons. We fill the octet around our chlorines. That uses 18 electrons. We have 2 electrons left, which we're going to put on the phosphorus to complete its octet. Now looking at this, we have to count electron groups. So any bond or lone pair is an electron group. So we have 4 electron groups. 3 are bonds. 1 is a lone pair. So if we look at the table, 4 electron groups, 3 are bonds, 1 is a lone pair. This would be trigonal, pyramidal. Trigonal pyramidal, that lone pair ends up repelling the bonds just a little bit. So if it was a perfect geometry of tetrahedral, our bond angle would be 109.5. Because we have a lone pair, the bond angle is going to be less than 109.5. Here's a practice for you to try. Figure out the molecular geometry and bond angles. Pause the video while you work. Silicon has 4 valence electrons. Each fluorine has 7. There's 5 of them. And we have a negative charge, which means we have 1 additional electron. We have 40 electrons to work with in our shape. So silicon, we're going to draw the fluorine around it. We know that there has to be at least 1 bond. So that uses 10 electrons to draw our bonds, 2 electrons in each bond. We add our valence electrons. That takes 30 electrons. We have 0 electrons left. So that means that there are no lone pairs on that center atom. We have 5 electron groups. All 5 of them are bonding, which means this is trigonal, bipyramidal. We have two different bond angles. So for the equatorial bonds, they are 120 degrees. And for our axial bonds, or between the axial and the equatorial bonds, they are 90 degrees. When we start looking at larger molecules, we can think of that larger molecule as being broken down into different pieces that have different molecular geometries around each piece. So we can think about it as having multiple central atoms. And we describe the shape around each central atom in sequence. So if we look at this particular molecule, and we can look at our first carbon, we see that we have 4 bonds around that center carbon, so 4 electron groups. And because it has 4 electron groups that are all bonds, this would be a tetrahedral shape around that leftmost carbon. If we look at the second carbon around our center carbon, we can count the electron groups. So in this case, we have 3 electron groups. We have 2 single bonds and a double bond that goes to the oxygen. So 3 electron groups. They are all bonds, which makes it trigonal planar. If we look at the last oxygen has 4 electron groups. Although they're not drawn, it does have 2 lone pairs on that center, or on that oxygen. So if we think about the electron geometry, it's trigonal, or it's tetrahedral. But our molecular geometry is bent because we have 2 bonding and 2 lone pairs on that oxygen. So this idea does extend to larger molecules. We just have to look at it a piece at a time.